Alright, so hello everybody. Let's talk about the third chapter. Obviously today being a snow day, we cannot do this in person, so I'm going to do this instead by a video recording. I'm going to talk a lot about how to do a hypothesis testing. We're going to talk about null and alternative hypotheses. So the idea here is in conducting research is how do you design it correctly so that you can actually get the results that you're at least attempt to get the results you're looking for, but find out whether or not your hypothesis can be supported or not. Let's talk a little bit about the whole process, though. So you start by finding research ideas. In general, we do it two different ways, or several different ways. One is through experiences. So either we have direct experiences that lead us to formulate our hypotheses. For instance, if somebody is suffering from a psychological illness, for instance, anxiety, their experiences with anxiety might lead them to propose hypotheses as to the causes or cures for anxiety. I also mentioned vicarious experience. Vicarious means learning through observation. So you observe the results that occur to other people and you learn from that. So essentially you might be seeing the effects of, say, alcoholism on somebody, of smoking on somebody. Some of my best research hypotheses have come from observing smokers. So I've kind of learned like, this is what they tend to do, so let's go ahead and test this. So that's not always derived from the literature. So there's this belief that we should always derive our hypotheses from prior research so we can have a very methodologically sound approach to generating hypotheses, but that's not the way the world always works. In general, it actually works by us focusing on our personal experiences and building hypotheses from our experiences and finding literature to support our experiences. However, we can also review the literature, and that is part of the research process. You do a lot of reading. What I mean by literature, of course, are the peer-reviewed articles. You do a lot of reading, and as you read, you come up with ideas. Also, researchers tell us about ideas that need to be investigated. In most articles, at the end, when you read the discussion, the researcher will give you a hint as to what needs to be done next. So that kind of gives you food for thought in formulating hypotheses. And of course, in reading the literature, we can also see if our hypotheses are novel, whether they've been done or not. And I put a frown face there because sometimes you get these great ideas, you think they're unique, but somebody's already done them. There's billions of people on Earth. It's not likely that your idea is novel, to be honest. All right, so the literature also provides us with other important information about research design, what kind of designs are prevalent in a particular area of research. Is it more experimental? Do you have experimental group control groups? Is it random assignment? Have most people done longitudinal or cross-sectional studies? What variables you need to control for? I look through the literature a lot when I'm conducting studies, and I decide what I need to control for. So if I'm doing work on smoking, generally I need to control for nicotine dependence, and there's a particular measure that everybody uses for nicotine dependence, and that's the measure that we'll tend to stick with because that's what I found in the literature. Looking for different methodological problems that occur when you're with different types of studying. For instance, different types of studies, For instance, I mentioned that defining smoking among adolescents and adults becomes very confusing as they are different. What's considered a smoker in an adult versus an adolescent is extremely different. Should we use BMI or lean body mass to measure obesity? There's lots of different questions that pop up as you read through the literature. And then, of course, for my part, it's identifying the best statistical methods. Sometimes, these days, people want to outdo themselves with the statistical methods they use in the old days, or among the less statistically educated individuals stick with ANOVAs and t-tests, which is not a bad idea. Sometimes simplicity is better, and general simplicity is better than complexity. But there are a variety of statistical methods that are prominent in a field or that are the state of the science at the time. And if you're not using those methods, you actually could be hurting yourself in terms of getting publications. In terms of using web sources for ideas, hey, web sources are very good, or web pages. But as you know, in this era of fake news, you have to be careful with who to believe, right? You don't want to believe just anybody. So just evaluate websites carefully before you trust them. There's some heuristics here to tell you how to evaluate a website. Look for the suffix. .com is not a good suffix because .com indicates business. Businesses have conflicts of interest, so if businesses are generally not going to provide you accurate information because they want to sell their products. .edu, you find that usually in institutions like LaSalle.edu, .org, .gov for government sites, those can be trusted more so than other sites. Check accuracy of credentials, including email address for contact. So you can actually follow up and see if the individuals who are the contacts are actually credible individuals. Objectivity, is the information provided objective? Are there biases? When people start expressing opinions, there's generally biases. How current is the website? So there's just a lot of information that you can look at. So are there fees required in order to get information? Fees aren't necessarily bad because, I think they are bad because everything should be free, but they aren't necessarily bad because in journals, we know that in order to get a copy of a journal article, in many cases you have to actually pay, so that's different. But what I'm talking about fees are the kind of, you can't see anything else unless you pay. That would be kind of bad. All right. You also want to look at whether your study is feasible. So in terms of generating the idea, you generate the idea. It seems like a very good idea. The next question, is it feasible? Well, what we mean by feasibility is, can it actually be done? Often we conduct focus groups prior to initiating a study to see if our activity is actually feasible. So for instance, if we say we're going to teach young adolescents meditation as a way to prevent violence, it is assumed that young adolescents would like to meditate, but that can't be assumed. So we conduct focus groups to ask young adolescents whether or not this would be feasible. Would they actually like to do that? So we have to always think about the feasibility of a study, particularly when we're trying to get money for our research by writing grants. And when we do that, we have to prove that our study is feasible. Can we complete it in a reasonable amount of time? Are there any ethical issues involved? How expensive is it for us to conduct a study? So these are all questions that we have to ask. The expense is real. This expense issue is real because not all studies are cheap to conduct. There are costs associated with conducting a study. If you want to accrue participants these days, especially in a city like Philadelphia, where there are many different universities, there's competition for scarce resources, right? So scarce resources are participants here, and there's competition for participants, so participants will naturally gravitate towards studies that offer money. So you have to be able to offer some kind of financial recompense for their participation. All right, so let's say we determined that our study is feasible. We have our idea, we determined that our study is feasible. The next step is to formulate the research question. Research questions are important. They shouldn't be vague. They have to be as specific as possible. Okay, so here's an example of a vague one. What effect does the environment have on learning ability? So you'd say, like, what the heck does environment mean? A better question is, excuse me, what effect does the amount of exposure to words at home have on the speed with which the words are learned? I mean, that's pretty specific there, right? And the specificity provides an operational definition of our variables. Our two variables here are environment, and the other is learning ability. What I did was I operationally defined them to make it a lot easier. So you want to make sure that you are extremely clear when you're operationally defining your variables. Generally, as you know, we have independent variables and dependent variables, and we'd like to specify those as clearly as possible. We may have other variables as well. As you know, we could have intermediate variables, which are those mediators, or we could have these moderator variables. If we have those, we have to specify them as clearly as possible within our research question. The next step we have to do is formulate our hypotheses. The important question with your hypothesis is, can it be refuted? So you have to be able to refute a hypothesis, right? So it has to be rejectable. In science, the pressure is on us, or the onus is on the researcher to demonstrate that the hypothesis is correct. It's not on the audience. We talked about pseudosciences before. In pseudoscience, the onus is on the consumer to prove that the item doesn't work or the hypothesis is incorrect. But in science, we put it on ourselves. So we start by formulating hypotheses that are rejectable. Now, a lot of these terms here should be familiar to you. So we have null and alternative hypothesis, because this has been covered in statistics before. But for review, the null hypothesis is the hypothesis we'd like to reject in favor of the alternative hypothesis. Generally, the null hypothesis will be something like, in this case, you have the mean for a placebo group is equal to the mean for the experimental group. In the case of, in this example here, we have a placebo, which is a sugar pill, and it's being compared to a drug like Paxil. Paxil is an antidepressant drug. So we're assuming that in this example that the placebo group is equal to the Paxil group in terms of mean for anxiety. So it's this example is a study to test whether or not Paxil helps reduce anxiety. Now let's look at this globally here. If I was actually doing a study to test whether or not Paxil works at reducing anxiety, I would do this study as follows. I'd have a pre-test where I would test participants in anxiety before receiving the drug or the placebo, and then I'd do a post-test, right? But at both times, I would be comparing the Paxil group to the placebo group. So what I'm showing you here in this area right here is actually the placebo versus the Paxil. So we're doing like a cross section. So we have the longitudinal part, which is the pre-test to the post-test, and then we have the cross-sectional part at each time point. At pre-test, we're looking at placebo versus Paxil. At post-test, we're looking at placebo versus Paxil. So that's the way we truly design a study. We'll talk about that kind of stuff later in the semester. But for right now, let's just focus on the cross-section here. Let's say we're doing post-test. And our null hypothesis is that the placebo is equal, the mean anxiety is equal in the placebo and the Paxil group, which is the same as the mean in the placebo group minus the mean in the Paxil group is equal to 0. My kitties are being bad right now, so I'm just having to watch them. I have two cats here. One male cat keeps on harassing the female cat. Jeffrey's harassing the other cats. I have to keep an eye on him. I don't know what his problem is. He's a young adolescent, or adolescent cat. All right, so we're looking at this specific situation here. Now, let me explain something about formulation of hypotheses. The most important hypothesis, even though we're interested in the alternative, which is the one, or what we call our research hypothesis, this null hypothesis is extremely important. Now you'll notice that we use Greek letters here in the hypothesis, right? The mu is a Greek letter that's a symbol that we tend to use for the mean, right? But it's for the population mean. So the Greek letters represent population values versus Latin letters. Like if I wanted to do Latin letters, I'd have an X with a bar over it. The reason we're using these these Greek letters is because we're talking about the population. So our assumption here is that when we're doing this test, everybody comes from the same population in the null hypothesis. So what does that mean? So in the beginning, we take people who have some kind of anxiety disorder, say social anxiety disorder, who are clinically anxious. They represent a population of clinically anxious individuals. What we're hoping is that after the drug, the people who are taking Paxil will be part of a new population called the formerly anxious, right? So they will not be from the same population as those who are clinically anxious. Okay? So that's what we're hoping. Now what we're saying here is that the population remains the same even after taking the drug. So that essentially the drug does not work. I mean, we may see some differences, but it's not statistically significantly different. So that's what we're saying with this hypothesis, is that even after the drug is given its time to work, everybody's still anxious. So that's what we're saying here in our null hypothesis. All right, let's move on. So in formulating our alternative hypothesis, so this is going to be a tricky part. Our alternative hypothesis can take on many forms. Let me check my next slide to see if So our alternative hypothesis can take on many forms. We can have our alternative being that, as it is here, that anxiety in the placebo group would be lower than anxiety in the, I think I have this backwards. This here, anxious participants taking Paxil will have lower anxiety. Actually, this, yes. So, but you look at my this should be backwards. So let me fix this for you all. Okay. Should be like, let's see, where is that on my computer? Here. Okay. This is what we should have. Okay. Anxious participants taking Paxil will have lower anxiety than participants taking the placebo, right? Because that's what we're hoping to find, right? So this is, you notice that we're specifying a very, very specific direction here for this result, because we're expecting, this is what we're hoping to happen. We're hoping that after taking Paxil, our population will have changed. Our participants will have been changed by the drug so much that they belong to a different population, individuals with lower anxiety. So that's what we're hoping will happen. I could also propose that, as I had before, I must have been showing this, that after taking the drug, I mean, it'll backfire and people taking Paxil will actually have higher anxiety than those having placebo. But that wouldn't really make sense for me to propose that unless I'm somebody who's working against Paxil and wants to show that their drug sucks. A third alternative is to say that, now I don't know if I have this on my, a third alternative would, it's probably here somewhere, let's see. So, insert symbol, there you go. Yeah, third alternative would just say not equal. There you go. I could just say placebo, the mean in placebo group is not equal to the mean in the Paxil group. This one seems to make most sense because it'll encompass everything. However, the decision whether to have a not equal or a greater or less than is extremely important. It's an extremely important decision because it's going to influence how much power you have in this study. Power is the ability to reject a false null hypothesis. You'll see that we have more power when we use what's called a one-tail versus a two-tail test. So what we're going to talk about briefly right now is the difference between a one and a two-tail test, and how does that influence power. And this is probably the most critical decision in formulating your alternative hypothesis. So there's two alternatives then. You're going to either go with the not equal, this is one option, like I have right here, not equal, or you can go with the other option, which is, so let me actually copy this slide, copy it and paste it here. So it's the identical slide, except for here we're going to go to this. Okay, so this is one alternative. So let's call this types of hypotheses. Alternative 1. So that's alternative 1. And then let's copy this sucker. Copy and paste it right here. The line is drawn here. There you go. Let's do alternative 2 be something like greater than, and then let's copy this sucker right here. Copy and paste. Okay. Alright, so this is our other alt. So we have these two different alternatives. So this is what we call two-tailed. Two-tailed. And this is one-tailed. And I'll tell you why that is in a moment. Alright, so this is your big issue here. Okay, you want to make sure that you have this correct. Alright? Alright, so what's the difference here? What's the difference? Why are you making us do this? Is this important? Let's see, do I have, yeah, that's not important. Okay, so let's take a look at this here slide from a different, from stats. If you didn't take stats with me, you wouldn't have seen this. So, bad luck, huh? Should have signed up for me. Alright, now this is your standard normal distribution. I will make a point here that we're just going to play with the standard normal distribution. The type of test that we're doing now wouldn't be using a z-test. It would probably be using some sort of a t-test, or actually more like it would actually be using an ANOVA. But we're going to just use the z-test as the simplest way to explain differences. Okay, because we know, and we could do the same with a t-test. But I have this really nice graphic of the standard normal distribution, which will help us understand why we do one versus two-tail test. Okay, this is a standard normal distribution. Each of the values associated with one of these sigmas here is a standard deviation. So this is the mean, and you'll notice that the mean is 0. And the standard deviations go out to the right and to the left, and they are negative on the left side and positive on the right side. Okay, so that's really important to know. You'll also note that this distribution is symmetrical. It's completely symmetrical. It means 50% of the distribution is below 0, 50% is above 0. Okay, so it's completely symmetrical. Some other important points: between 0 and 1, standard deviation above the mean is 34.13% of the population. The entire population, 100% of the population, resides underneath this curve. So all these values are, like for instance, this is the most frequently occurring value, also known as the mode, right? And you can see that by the size of this hump here, it's highest at 0. That means that's where most of the values occur, because that's at the mean, mode, and median are the same when it comes to the standard normal distribution. So below the mean is 50% of the population, and above the mean is 50% of the population. Between plus or minus 1 standard deviation is 68.26% of the population. Between plus or minus 2 standard deviations is about 95% of the population, and so on. Okay, this is very, very important to remember. All right? All right. So when I am conducting hypothesis testing, I always assume that the null hypothesis is true. Okay, and then I'm going to judge how far my calculated value is from the mean. Okay, and that'll help me determine whether my conclusion, my alternative, what my conclusion is significant or not significant, right? How do I judge whether something is significant? Well, it's significant if it's highly unlikely to occur given that the null hypothesis is true. Given that most values occur between plus or minus 2 standard deviations of the mean, 95% of all results will occur within plus or minus 2 standard deviations of the mean. 95% of all values of our test statistic, in this case, this is a standard normal distribution, so we'd use a z-score, right? You see that the z-scores are exactly the same as the standard deviations, right? So any calculated test statistic value that falls further away is highly unlikely to occur, given that the null hypothesis is true. Okay? So that's what you have to remember. Given that the null hypothesis is true, how likely is something to occur? Okay? That's what we're asking. If it's highly unlikely to occur, it's very unlikely to have occurred by chance alone. Or in other words, it's very unlikely to be a mistake, right? So when we set our alpha is a probability of a type 1 error. Type 1 error is a false positive result. So alpha is the probability of a false positive result. That alpha level is some probability value. Generally in science we've been using alpha of 0.05, but that's not written in stone, or whatever you say. You can change that alpha depending on a whole bunch of situations. I mean, if we're not dealing with a dangerous conclusion that could be harmful, we could set our alpha to be larger, like 10% instead of 0.05. If we're dealing with a high stakes, if we're doing a high stakes study of some sort, then we want our alpha to be lower because we want the probability of a type 1 error to be lower. Let's say we set our probability of a type 1 error to be 5%. That means we only want a 5% chance of a false positive result, and we want 95% confidence that we don't have a false positive result. Well, if we want to know where 95% of our population resides, so we'll follow these percentiles. Percentiles is we're going left to right here. So the 95th percentile is somewhere around here. And on the z distribution, I believe it's 1.684, value 1.684 or higher. So it's like right here, right? So any value falling above 1.684 would be highly unlikely to occur because it would only occur 5% of the time, right? Because if we're looking at this distribution here, and only 5% of the population, starting from negative infinity and moving up to the right, a value of 1.684 or higher would only happen 5% of the time or less. Okay, so it's very unlikely to occur by chance alone, right? So that means it's very unlikely to be an error. So if we set our threshold for a mistake to be alpha equals 0.05, any value smaller than that, right, 0.05 or smaller, would be very highly unlikely to occur by chance alone if the null hypothesis is true. So it means it's unlikely to be a mistake. Okay, so that's what alpha means. Now, that would be a one-tailed test, right? Because all 5% of the distribution is to the right. In this case, to the right. So this would be equivalent to saying that, let's go back to our previous slide. That would be equivalent to saying that our anxiety in our Paxil group is less than our anxiety in our placebo group, right? So if we go back here, earlier, let's see, here. Our null hypothesis was placebo minus Paxil group is equal to 0, right? If our alternative is that the anxiety in the Paxil group will be lower than placebo minus Paxil will be positive, right? Because you'd have a higher anxiety in the placebo group and lower anxiety in the Paxil group, right? So it would be positive. So if it's positive, we're going to work with the right side of this distribution. Notice that all the plus signs, it means all the values are positive to the right. If, on the other hand, we had said that the effect will be negative, right? Like we hypothesized that individuals with taking Paxil would have higher anxiety after the test than individuals taking placebo. Our value would be negative, so we'd be looking at the lower 5% of the distribution. So our criterion then for rejecting the null hypothesis would be any calculated z-value less than negative 1.684, right? So it would be the lower 5% of the distribution. Okay, now, if we choose the other alternative, right? Remember we had a second alternative here, that the two groups are just not equal, right? The two groups are not equal. That means, going back to our figure, that means that either the Paxil group would have lower anxiety than the placebo group, so placebo minus Paxil in terms of anxiety would be positive, so the result could be up here, or it could be the other way around where the Paxil group could have higher anxiety than the placebo group, so placebo minus Paxil would be negative. So it could be over here. So we're not really sure. Because we're not sure and we set our alpha at 0.05, means there's a 5% chance of a type 1 error, we have to divide that 5% in two and put 2.5% up here and 2.5% up here. Well, this is already done for us because we know 95% of the population resides between plus or minus 2 standard deviations. Actually, it's 1.964. So any value above here or any value below here would be considered significant. Any calculated z-value, that is. Okay, so any calculated z-value above, just say 2. For simplicity, let's say 2. Any calculated z-value above 2 or below negative 2 would be considered significant. Or, since 2.5% of the population resides here, or 2.5% and 2.5% of the population resides here, any probability value lower than 0.05 would be considered significant because half of the distribution is here and half of the distribution is here, right? 2.5 plus 2.5 is equal to 5%. Now here's the interesting issue in relation to 1 versus 2-tailed tests and why the decision is so important. With the 2-tailed test, because we split the probability between the upper end and the lower end of the distribution, our critical value, that means the value, our threshold for determining significance is the absolute value of 2, right? So it's either plus 2 or minus 2. It means only values that are calculated, z-values calculated, that are greater than or equal to 2 or less than or equal to negative 2 would be considered significant. All right? So it means you have to climb, imagine you're climbing a ladder, and in order to achieve safety, you have to go above 2 rungs of that ladder. That's the only way you could be safe, okay? If, on the other hand, we did a 1-tailed test, look at this. Our threshold moves from 2 down to 1.68. So it's a little bit lower, right? A little bit lower. By being lower, that means we would be safer on that ladder, climbing a little less higher than if our threshold was 2. So with a one-tailed test, you're more likely to reject the null hypothesis than with a two-tailed test. So you have more power. So making that decision to use either a one or a two-tailed test is very important in terms of having power, the ability to reject a false null hypothesis. Okay? So that's a crucial decision to make. So again, let's just recap. You have more power if you use a one versus a two-tailed test. However, the important thing here is that you have to make that decision in advance. You can't make that decision late, after the fact. Because like, let's say you do a two-tailed test, right? And you fail to reject the null hypothesis because let's say your calculated z-values 1.87. Well, that's less than 1.964, right? So you fail to reject the null hypothesis. Then you say, oh boy, guess what? If I did a one-tailed test, my criterion for rejecting a false null hypothesis is only 1.68. And my value is 1.8 something, I can reject it. So you can't do that. You can't go after the fact. That's a bozo no-no, as they say when I was young. All right? All right, so just some conventions for null and alternative. Null is generally written H sub 0 and alternative H sub 1 or H sub A, something like that. And let's see, anything else I want to talk about? That's pretty much it. So you're going to end up picking the statistical method that best fits your research, but the ultimate goal is to start by formulating the research question well, formulating the appropriate hypotheses, and thinking carefully through your decision in terms of how to formulate that alternative hypothesis. So the research design, every bit of the process is extremely important. You can't just neglect any one of them. Okay, that's it, folks. I'll hope this helped, and enjoy the rest of your day. Thank you very, very much. Bye.